Well, we'll start with binary arithmetic today. So as all we know that binary arithmetic includes binary addition, subtraction, multiplication and division. So for our digital electronics, let us go with binary addition and subtraction procedures. So the word binary addition means addition of two binary digits instead of binary numbers. Let us start how to add two binary digits. So for performing the binary addition, firstly, we need to know the truth table for addition. Right, if I consider A and B as two bits and A and B can have two combinations, either A can be of 0 bit or else B can be 0. So by considering all this, we can frame different combinations for A and B like 00, 01, 10 and 11. Now coming over to the first bit addition, that is with A0 and B0. When we perform addition, you know that the output will be as a sum along with a carry. Now, when A is 0 and B is 0, the resultant sum will be 0 along with the carry. There will not be any carry generated. So, carry also becomes 0. When we perform addition of a bit 0 and 1, 0 plus 1 will become sum 1 and no carry is generated. So, carry is also 0 again. Now, coming over to 1 plus 0, sum will be 1 with again carry 0. But when the addition of two bits, that is higher bits with A1 and B1 is considered, then 1 plus 1 actually in our decimal number system, it will become 2. As the binary form of 2 is nothing but 1, 0, where the least significant bit will come under the sum and the most significant bit will come under carry. That's the reason 1 plus 1 clears us that some resultant will be 0 with a carry 1. So if I consider a small example, that is if I want to add 1010 plus 0101. So here bit by bit addition will be performed and that too from LSB bit to MSB bit. So coming over to first LSB bit 0 plus 1. From the truth table you know that 0 plus 1 is sums 1 as well as carry 0. So sum 1 and carry 0 will be carried out to the next bit addition. Similarly 1 plus 0 again 1, 0 plus 1, 1 and 1 plus 0, 1. So in this way, the help of truth table for binary addition, you can perform addition of any number which can be represented in its respective binary forms. Now coming over to the next binary arithmetic process, that is binary subtraction. Similarly, let us start the subtraction with 2 bits. Let us consider A bit and B bit. Again, 2 bits means there will be 4 different combinations that can be framed. Either the bit A can be 0 or 1 as well as B can be 0 or 1. Based on these two combinations, there will be 4 types. I mean, with AB 00, 01, 10 and 11 different combinations. Now, when we perform subtraction, we know that the resultant is named as difference, and the subtraction of the smaller number from larger number will be easy, but subtraction of larger from smaller considers another term which is known as a borrow. So A and B will act as my input and the outputs for binary subtraction will be a difference and borrow. Coming over to the first combination with A0, B0. So 0 minus 0, it results a difference 0 and there is no borrow. That's the reason borrow has become 0 again. 0 minus 1. So let us wait until we complete the remaining 2 and we will move on to this second combination. 1 minus 0, that is 0 bit is subtracted from 1. So the difference will be 1. There is no borrow generated, so borrow will be 0. 1 minus 1. As we know, the difference results 0 as well as no borrow, so 0. So coming over to the special consideration, that is if a larger number gets subtracted from a smaller number. You know, normally in decimal subtraction, if it happens, the resultant will be in negative. So coming over to binary subtraction, instead of using the signed and unsigned concept, here directly with the help of truth table, we can identify what can be the borrow as well as different when 1 is subtracted from 0. So 0 minus 1. So I can't subtract 1 from 0. That's the reason we are taking a borrow 1. So here, in case of decimal subtraction, borrow indicates that gets added to the original input bit. But here, borrow will be placed at the second position of your LSB bit. So if I take borrow as 1, so that 1 will be placed in the second position after LSB bit. So LSB bit is 0 and the next bit to the LSB bit will become 1. So we know that 10 is the binary form of decimal digit 2. So now the subtraction continues as 2 minus 1. It results 1. That's the reason 0 minus 1 gives a difference 1 with a borrow 1. So this is the truth table we have to remember for binary subtraction. So as we said, two types of subtraction procedures will happen. That is subtraction of the larger number from smaller number as well as subtraction of smaller number from larger number. So in the case of subtraction of smaller from larger, using the truth table concept, it will be easy for us. But there will be a difficulty while performing the subtraction from larger, that is larger number getting subtracted from a smaller number. Why? Because considering the borrows as well as placing their locations and taking the values, it will be a bit difficult task for us. So to make simplify or to simplify the subtraction operation, we are going to consider the concept called as complements. So finally, complements are nothing but the procedures of subtraction where you are going to make the subtraction procedure easy, right? So let us discuss what are these complements first. So coming over to complements, you have understood that complements are nothing but these are the process, or this is the process used for performing subtraction. As we said, subtraction will be a bit difficult with the help of truth table concept. Again, if I use the same concept of truth table for complements, so what's the use of moving on to complements then? That's the reason here complements will be the process of subtraction, but which doesn't involve any truth table concept of subtraction. So it is going to involve the truth table concept of addition. Why? Because addition using the truth table is easy for us instead of going with the subtraction truth table, right? So complements are, these are the process of subtractions where we use additions internally. Right, so two types of complements of numbers can be identified. They are diminished radix as well as radix. Here already we know that radix or the other name for radix is base. So what does this radix or base define us? It is going to say about the type of number system. What type of number system we are using. For suppose if the radix is 2, it comes under binary number system. If the radix or base is 8, it is known as octal. So based on the value or based on the representation given for the radix, we are able to identify what type of number system we are using, right? So for our digital electronics, as already we have discussed that out of many number systems, 4 particular number systems are get involved. They are binary, octal, decimal, and hexadecimal. So here we are fixed to the value of that radix, that is from 2, 8, 10, and 16. Then other radix is also being taken now, which is known as diminished radix, where it becomes 1 less than the radix, that is r minus 1. For suppose if radix is represented as r's complement, then diminished radix will be represented as r minus 1's complement. So for all the type of number systems, whatever we have used so far, there exist two types of complements, radix complements as well as diminished radix complement. So coming over to the binary number system, as the radix is 2, so diminished radix will become 2 minus 1, that is 1. Therefore, 2's complement and 1's complement will exist for binary number system. Coming over to decimal system, the R value will be 10. So diminished radix will become 10 minus 1, that is 9. Therefore, for a decimal number system, 10's complement and 9's complement will exist. Similarly, for octal, 8 and 7's. For hexadecimal, 16 and 15. Now coming over to the first, that is binary subtraction using complements concept, as the radix value is 2 and diminished radix is 1. So there exist two types of complements to perform subtraction of binary numbers, which are known as 1's complement and 2's complement. So let us start with the 1's complement first. So generally this 1's complement representation is nothing but simple. We are going to interchange zeros in terms of 1's and 1's in terms of zeros. So replacing the value of 1 with 0 as well as 0 with 1 is done with 1's complement process. But suppose let us consider an example, 10110. So 1's complement of 10110 will become 1 replaced by 0, 0 replaced by 1. So 01001. Right? Now this is 1's complement. Just remember that 1's complement is interchange of 1 to 0 as well as 0 to 1. Next coming over to 2's complement. So 2's complement is obtained by adding 1 to 1's complement. So for the given binary form, you have to perform 1's complement first. Then to that resultant, if you add 1, then that gives us 2's complement. And addition of 1 will be at your LSB bit, not at your MSB bit or anywhere in between. So always adding this 1 must be done at your LSB bit, right? So now we are in a position to find the 1's complement and 2's complement form of the given binary, right? Now using this complement, let us see how the subtraction procedure will continue with binary, right? Now let us see the subtraction of number using 1's complement, right? So 1's complement method is going to describe to perform subtraction using only addition. And two cases as usual we have discussed so far, that is subtraction of the smaller number from the larger number and larger number from the smaller number. So coming over to the first case, that is subtraction of smaller from the larger. So here we are going to follow a 3-step method for performing this 1's complement subtraction on binary number. That is first step, you have to identify the 1's complement of the smaller number. For suppose if a minus b, then here b becomes a smaller number, a becomes a larger number. Why? Because b, the case is like subtraction of smaller from the larger. So you are going to find the 1's complement of the b digit, right? So then after, add the 1's complement of the smaller number to the large number. So after taking the 1's complement of b, you must add it to the binary form of a. Then, you know, if you perform addition, there are chances of carry generation, right? At that moment, if carry is generated, you have to remove the carry and add it to the result. Remember here, always adding will start from LSB, I said, right? So let us see one small example. So I'm going to subtract 0101 from 1100. So you know that 0101 is a binary form of 5 and 1100 is a binary form of 12. So 5 is getting subtracted from 12. So the resultant must be what? 12 minus 5, that is 7. Let us see, will it be obtained or not? So coming over to the smaller number is 0101. What's our first step? You have to determine 1's complement of the smaller number. So what is 1's complement of 0101? It is 1010. Then after you have to add it to the larger number. The larger number is 1100. So you have to add this 1010 to 1100 using truth table concept of your binary addition. Let's start adding that. So 1100, 1010, 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1. And coming over to the last case, 1 plus 1. You know that sum 0 with carry 1. So sum is placed at the bottom and carry will be at the next bit level. So there is no further addition process. For suppose if you have further bits over here, then this carry will get added to that sum, right? So as it got stopped here itself, final step will be what? That carry will fall down in the result. Now what is the third step? If the carry is generated, you have to remove the carry and add it to the result. So I'm going to remove this carry and add it to the result at its LSB position. Now perform addition again. So 0110 plus 1, what it becomes now? 1110. So what is 0111? It is nothing but equivalent to 7. So our subtraction procedure using complements, that is which involves addition, is but fine. Okay, this is the way we have to do 1's complement subtraction. Similarly, subtraction of larger number from smaller number. This time same procedure must be applied, but you have to concentrate on b always, that is a minus b, which is getting subtracted from what? Always perform the complement process on that, right? So the subtraction of larger number from smaller number means you have to determine 1's complement of larger number, then you have to add it to the smaller number. Right. So in this case, there will not be chances of carry generation. Why? Because you know that when a larger number is getting subtracted from smaller number, generally we prefer borrow. But in the case of addition, there will not be the concept named as borrow. We will have only carry. So it is very clear, like in the third step, there will not be any carry generated. You will have only final result after adding this 1's complement of larger number and smaller number. So what we say here is, we say that the answer is in 1's complement form. Why? Because already 1's complement of one of the number is being performed. So that is not the actual number for us. That's the reason we say the resultant answer is in 1's complement form. So to get back to your original or true form, you have to take 1's complement of the answer and assign negative sign. The reason to assign negative sign is the basic concept. Larger number, when it gets subtracted from the smaller number, the result will be a negative number.